Our most recent videos have dealt with parametric equations. Today's video is also going to deal with parametric equations. In particular, we're going to talk about types of calculus questions that we can answer in the setting of parametric equations. And in the process, we're going to have an opportunity to review a good bit of the material that we covered at the beginning of this semester. Let's go to the whiteboard. So all of our examples today are going to deal with the cycloid, not because there's any particular special weight that I would like to give to the cycloid, but simply because the cycloid makes a nice, clean example that turns out to have some interesting properties. So it's not the cycloid that we're really interested in, it's the calculus that we're performing using the example of the cycloid. So as a reminder, here are the parametric equations that we developed several videos ago that gave us this curve that we called the cycloid. And what we'd like to ask first today is, what is the area that is between the graph of the cycloid and the x-axis over one period of the cycloid? So as a review of some of the material we did at the beginning of the semester, the first thing we're going to do is to dissect this region, and we're going to dissect it into rectangles. After we dissect, we're going to analyze the area of a typical rectangle, and pretty straightforward, right? The area of a rectangle is going to be the height times the width, and in this case, we can see that the height is given to us by the y-coordinate that is given to us by the rectangle, and the delta x sub I, the width of that rectangle, is a little change in x. All right, so we've dissected, we've analyzed, and now we want to reconstruct. So the area of the region we can approximate now by putting all of these pieces back together, putting all of the areas of the rectangles back together, and that gives us this Riemann sum. Well, fortunately, we have a way of deciding on the quantity that is being approximated by a Riemann sum. You may recall that if we can approximate a quantity by the Riemann sum of some function, then we can calculate that quantity precisely with a definite integral, right? That's basically a rewording of the fundamental theorem of calculus that Isaac Newton and Gottfried Leibniz gave us in the 1600s. So here we go. So the area of the region then is going to be, well, it's going to be the integral of the function that we were using in our Riemann sum. So y dx, and x is ranging from, let's see, it's ranging from 0 to 2 pi r. You might recall that the one period of the cycloid, recall that it's generated by taking a circle and looking at a point and following that point as the circle rides along a curve, and by the time the point comes back to here, the entire circumference of the circle has ridden along the x-axis, and so the circumference of the circle being 2 pi r gives us the range of x values that are being traversed for one period of the cycloid. So we're going from 0 to 2 pi r, and here, so far nothing has changed. Everything is exactly the same as what we were doing at the beginning of the semester. Only now, since we're working in the parametric setting, we'd like to translate this integral from values of x to values of theta, the parameter that we're using in our parametric equations. Well, that's pretty straightforward, right? Y in terms of theta is just r times 1 minus cosine theta. We're just copying down the value of y. dx you'll recall is, well, the differential of a variable is equal to the derivative of the function defining that variable times the differential of the independent variable. And so the derivative of theta minus sine theta is 1 minus cosine theta. And so we have a constant in front of that. So dx is going to be r times 1 minus cosine theta d theta. And so we'll just put all that back together again. So in place of y, I'm writing r times 1 minus cosine theta. In place of dx, I'm writing r times 1 minus cosine theta. So that's going to give me r squared times 1 minus cosine theta squared d theta. So we translated the integrand from x's to thetas, but we also have to translate the range of x values to a range of theta values. Right? We want to translate the entire integral to thetas, and as the circle traverses from here to there, the circle has gone exactly one complete revolution. So theta has gone through a total of 2 pi radians. So we're going from theta being 0, whenever x was 0, to theta being 2 pi when x was 2 pi r. And so this is the integral that we wind up with. And I've evaluated that integral on the next page, but before we look at that, I would encourage you to pause the video and see if you can work this integral out on your own as a review of some of the material we did toward, I guess this would have been the second chapter that we covered this semester, the chapter on integration. Go ahead, give it a try. Okay. Were you successful? Right, so here's what you were integrating. And tell you what, I'll just show you my work. And I'll let you look at that for a bit. Why don't you pause the video while you study that? Okay, so were you successful? Did you come up with something similar to what I got? I think the only somewhat tricky thing was finding the antiderivative of cosine squared. So if you remembered this trigonometric identity that cosine squared theta is 1 plus cosine 2 theta over 2, then you were probably able to get the rest. What's interesting about this answer, it really is a very interesting answer if we put it in context. Without the 3 there, what I've got is the area of the circle of radius r. In other words, the radius of the circle that the area of the circle that generated the cycloid. Right? It was generated with a circle of radius r. And so what we have is that one period of the cycloid, the area under the graph of one period of the cycloid, turns out to be exactly 3 times the area of the generating circle, which I think that's just fascinating, that it comes out that cleanly. Okay, let's look at another example. Let's switch from area under the curve to arc length. And we will ask, well, what is the length of the arc of one period of the cycloid? So again, I have the equations of the cycloid here for reference. And this also is going to look very similar to what we did whenever we studied arc length earlier. In fact, most of what we do in the parametric setting is going to be identical to what we did whenever we were looking at a curve as the graph of a function. So I've labeled. So I've dissected the arc into straight line segments. So I've drawn a typical line segment there, and then I dropped an altitude down and brought a base over to create a right triangle with that line segment as a hypotenuse. And I'm going to use that to analyze the length of that typical segment. Well, it's just kind of screaming at us, isn't it, that the Pythagorean theorem can be used here to put these three pieces together. So the length of the hypotenuse squared is it's going to be delta x sub I squared plus delta y sub I squared, right? Simple Pythagorean theorem. And so taking square roots gives me a way to express the length of that line segment. Okay, so what? Well, you may recall last time, so we know that eventually we want to get a Riemann sum involved. And so it would be nice to have a delta something sitting out here. Whenever we were working in functional notation, we wanted a delta x out here. That's what we wished for. And now, because we're working in the parametric setting, it might be more reasonable to wish for a delta theta to be sitting out here multiplied by some function. And so, well, as we've said before, if you want something, make it happen, and then deal with the consequences. So let's put a delta theta, and I'm going to put a little sub I there because our thetas are going to change as our interval changes. So multiply by a delta theta and divide by delta theta. Of course, if I divide by delta theta, I can bring that delta theta inside the radical sign as a delta theta squared, and then separate the fraction into two fractions. So look what I got. So I've got delta x sub I over delta theta sub I quantity squared, and I've got a delta y sub I over delta theta sub I quantity squared. Well, let's focus right now on the delta x sub I. So if I had a graph of the function that was giving me x, if I had a graph of this function up here, and I looked at so let's say this is the interval that we were working on. So delta x over delta theta is describing the slope of a line between 2 points. And we've described this before. If I take that line segment and I keep the slope the same, but slide it off the graph, there's some last point at which it's going to hit. And so at that point, that line, that slope is, well, it's still going to be delta x sub I over delta theta sub I because I didn't change it, but that's also going to describe the slope of the tangent line at that point. So the slope of the tangent line is going to be delta x sub I over delta theta sub I. But the slope of the tangent line is also the derivative of the function. And so I'm going to replace delta x sub I over delta theta sub I with the derivative at whatever that theta sub I is that I hit whenever I slide the line segment off the graph. And I'm going to do exactly the same thing with the y variable. So delta y sub I over delta theta sub I, that's going to, by the same sliding motion with the y graph against theta, I'm going to be able to translate that into y prime of theta sub I. And we're squaring both of those quantities. And so this gives us a nice way of expressing the length of that line segment. Okay, so I've dissected into straight line segments. I've analyzed the length of a typical segment, and now I'm going to reconstruct. So the arc length is going to be, well, it's going to be the Riemann sum of the expression that I got for delta S sub I. So next thing we're going to do is use the fundamental theorem of calculus. right? And recognize that the arc length is simply going to be now the integral of the function that we got before. So if you will, at this point, pause the video and see if you can evaluate that integral. Be great practice. At least see how far you can get. Go ahead, I'll wait. Okay, so how'd you do? Were you able to solve the integral? Well, let's see what I did. In fact, let me just pull all this off, and then we'll I'll tell you what, why don't you pause the video again, take a look at my work, and see if you can follow it, and then I'll come back in and explain some of the trickier points. Go ahead, pause the video. Okay, so I'm betting that you probably were able to recognize that with this r being a constant, and it's being squared in both cases, I can factor that r squared out, but then I can factor it outside the radical sign as just an r. And then we have the rest of the expression. I went ahead and expanded 1 minus cosine theta. And then I recognized that cosine squared theta plus sine squared theta was just 1. And so what I have is 1 plus 1, 2, minus this 2 cosine theta under the square root. And just for convenience, I thought it would look prettier if I had a 1 minus cosine theta sitting there. So I factored my 2 out and then brought it outside the radical sign as a square root of 2. My next step is the trickiest, right? How am I going to evaluate the square root of 1 minus cosine theta? I'm probably going to need some trig identities, and I can think of a couple ways out of this conundrum, but I think the cleanest way out is to recognize that, this almost looks like part of the identity for sine squared of theta, except I would have needed a 2 theta in there, and I'd need a 1/2 as well. But what I did is just said, well, if I were looking at 2 times sine squared of theta over 2, then I'm just copying my 2 down here, and I'm multiplying by, well, let's see. So sine squared of a thing is 1 minus cosine of twice that thing. Well, twice theta over 2 is just theta. And then all that over 2. And so what I wind up with is that 2 sine squared theta, right, what's under my radical sign, is just 1 minus cosine theta. So I can replace 1 minus cosine theta with this expression. And that's very nice because now I've got the square root of a sine squared. And on the interval that I'm working on, 0 to 2 pi, theta over 2, let's see, theta over 2 on this interval is going to be ranging from 0 to pi, which sine of angles between 0 and pi are always positive. So whenever I take the square root, I'm going to get exactly sine of theta over 2. And of course, I also took the square root of 2, and I factored that outside the integral sign and multiplied it by the square root of 2 that I already had to give me a 2. And so I wind up just integrating 2r times, well, my answer is going to be 2r times the integral 0 to 2 pi of sine theta over 2 d theta. And that has a pretty simple integral. But the answer turns out to be very interesting. The answer of 8r tells me that, tells me that the length of one period of the cycloid is exactly 8 times the radius of my generating circle. or if you like, 4 times the diameter. So if I took my generating circle and looked at the diameter of it and placed that diameter on here, I'd be able to place it on here 4 times, and I'd have exactly the length of the cycloid. All right, final example. We've done area, we've done arc length. Let's do volume. So let's take this cycloid, let's take one period of the cycloid, the graph of it, graph of one period of the cycloid, and let's revolve it around the x-axis. I've only drawn a piece of that, right, and drawn a piece of the shapes that I'm dissecting this into. So I'm going to dissect this volume, this solid, into a bunch of circular cylinders, discs with a little bit of thickness to them. And then I'm going to analyze the volume of a typical cylinder. Well, that's pretty straightforward, right? We did that toward the beginning of the semester. We got pi times the radius squared times the width, right? This is the area of the circle, the face of the cylinder, and then multiplying it by the width of the cylinder. And let's see, so my radius of my cylinder is just the, so we're going from y equals 0 to y sub I. And so the radius is just y sub I. The width I've indicated as a change in x. And so I can express the volume of my cylinder in this way. And so then we can reconstruct. If I put all of those pieces together and add up all of those volumes, I get a Riemann sum. Well, again, if you can express a quantity with a Riemann sum, approximately with a Riemann sum, then you can evaluate it precisely as a definite integral. And so that's using the fundamental theorem. And so the integral is going to be 0 to 2 pi r of pi y squared dx. And if I translate that, and again, so far we haven't done anything differently. Everything is exactly the same as it was toward the beginning of the semester. Here's where this next step is the only thing that's going to be different, right? We want everything in terms of theta, in terms of the parameter that we're using. And y is explicitly given to us right there. And dx we're going to get in the same way we got it before. We're going to just take the derivative of the function and multiply d theta by it. And by definition, that's our dx. And so that's the translation of the integral to from x into theta. And we also have to worry about the limits of integration, right? These are values of x. And so we have to translate those to values of theta. But again, whenever x was 0, the circle had not spun at all yet, so it had gone through 0 radians per revolution. By the time we revolved it so that the point that was there is now here, the circle has gone through a full revolution, so a full 2 pi radians. So theta is 2 pi at that point. And so if I simplified that just a little bit, what I wind up with is that the volume of the solid is being expressed by this integral. I have solved this integral for you. I'll show it to you in a moment. I'd like you to pause the video for a moment and see if you can evaluate it on your own. I'll wait. Okay, how'd you do? Let me just show you my work. Here we go. So first step that I took was to, well, after bringing r cubed outside the integral sign, since it's just a constant, let's just get it out of the way, I expanded the expression 1 minus cosine theta quantity cubed. And so I get this. Once we have that, let's see, the first couple of pieces are very straightforward. We already integrated cosine squared a little bit earlier. I have the integral of cosine squared written down here. The integral of cosine cubed, well, one way to get at that, and the way that I think that we typically did it earlier in the semester, was to break it up as cosine squared times cosine, but then cosine squared is 1 minus sine squared theta. And we can evaluate this with a substitution by letting u be sine of theta, and then du would be cosine of theta d theta. So whenever I integrate that, this is the antiderivative that I wind up with. And so putting all this together, I wind up with the integral equaling 5 pi squared r cubed. Not nearly as satisfying as either of the other integrals. It doesn't really seem to give us any clean association with the generating circle, or even with the sphere of radius r that we might be able to put inside. I mean, we can find a relationship, but it's just not as satisfying. So, but it is the answer. That's the integral. That's the value of the volume of the solid that we get whenever we take one period of the graph of the cycloid function and revolve it around the x-axis. And that concludes our series of videos on parametric equations. In our next video, we're going to look at polar coordinates, and eventually we're going to do some of the stuff we did today, finding areas, finding volumes, finding arc lengths in the setting of polar coordinates. Until then, stay safe. I'll see you then.